Did everybody catch on to all of that? Now, this circuit and what we're going to do is going to be a little bit of a lie, and it's intentional. But I want you to do what you think would work out. So I'll say it again. We're going to close switch A, that is time equals 0. And then I want you to find the instantaneous current in the bottom resistor, and then the long-term current in the bottom resistor. In the circuit, switch A is closed at time equals 0. I want the instantaneous current through the 12 ohm resistor and then the long-term steady state current through the 12 ohm resistor. Okay, give it a try. See what you can knock out here. These are pretty straightforward. They're not terrible. And again, just to time equals 0, it gave us a current of 3/2 amps. Oop, not 3/8, 3/2 amps. And then T infinity, the current was 8/5 amps. At infinity, remember, you treat this like it has 0 resistance. So it's the 12 and the 4 in parallel. Reduce that first, and then add it to the 12, and it's 24 divided by that. Pretty straightforward, I think. So these aren't terrible. And again, a lot like the capacitor ones. Here's what I want to really take a look at today. And I'm going to write this circuit out because I want you to see it that it can be done 2 different ways. This is the first way you can see this circuit with something we talked about yesterday called a make before break switch. A make before break switch allows you to make a new connection before the old connection is broken. So this is one way to build this circuit. And I'm intentionally leaving out a resistor, even though that's not particularly realistic because the wires would then become the resistance. The other version of this circuit, and they serve the same goal. And there's a way to make this circuit with just one switch, but I'm doing it this way on purpose, kind of. So, in the circuit, oops. Need another switch here just to make it clear. There. In both of these circuits, you can isolate either the capacitor and the inductor with the EMF. So in the circuit on the left, if I want to isolate the inductor, I leave this switch in open position, and I move the make before break switch to the A position. This would allow me to charge up the inductor on its own. On the right circuit, I close switch A, leave switch B open. That isolates the capacitor with the EMF, and that would charge the capacitor up. On the make before break side, I can slide my make before break switch from A to B right after I close switch A. That means that I am removing the EMF from the circuit and beginning a circuit where all of the energy is in the inductor. On the capacitor side, it's easier to do this because the timing doesn't have to be special. I can open switch A and then close switch B. When I do that, I have all the energy in the capacitor, and then I close switch B, which allows the energy in the capacitor to be passed to the inductor. Regardless of which one of these 2 circuits we look at, what I want you to understand is the energy in a circuit like this can transition from the capacitor to the inductor and back. We're going to use this as our circuit because it's just easier to understand. And I want to start by saying we close switch A and let the circuit come up to a full charge condition, which means that after a long period of time of switch A being closed, our capacitor becomes fully charged. So we reach the state where the charge on the capacitor is going to be C times the EMF. This is at steady state. I'm intentionally using an uppercase Q to represent the maximum charge on the capacitor. All good? Any question about that? Good. So we can then, the capacitor is fully charged. I close switch B, and we have a Kirchhoff loop in here. In our Kirchhoff loop, we'll have the voltage drop across the capacitor and the voltage drop across the inductor equals 0. Now, if we're looking at the state of this problem, the voltage drop across the capacitor is going to be based on the charge of the capacitor. But do you realize the charge in the capacitor is not going to stay a fixed value for very long? The charges are going to attempt to equalize, and they have the possibility of running through the inductor when they do. But the inductor is going to present a back EMF, which is going to hold the charges in place instantaneously and then allow them to start moving through the circuit, increasing their current over a period of time until we reach a point of maximum current in the circuit. During that time, all of the energy will be switched over to the inductor. But then the inductor is going to begin to collapse, and the magnetic field is going to push those charges onto the capacitor until all of the charges have switched sides, and now the capacitor is fully charged. This is a simple harmonic oscillator, and the energy will oscillate back and forth between the capacitor and the inductor. You have the capabilities to solve this problem, but it's probably at the top end of your capabilities. So let's take a look and see what this would look like as a differential equation. And for you guys who have had mechanics, this should appear familiar. For you guys who haven't had mechanics or in mechanics right now, we won't see this until, well, April at the rate we're going. So the capacitor, negative Q over C. I used the lowercase q to indicate this is Q as a function of time, minus my inductor, which is defined as L di dt, which equals 0. Now, di dt is based on the rate of change of current, but current is its own differential. It's dq dt. So I want to get this all in the terms of a single variable, so I'm going to get the whole thing in terms of Q. That means I have negative Q over C minus L times the derivative of Q with respect to T. You've seen this before, I'm aware, right? How you're supposed to write a second derivative. Everybody in mechanics should know it because we did it last year, but if you haven't done this before, the symbology is a little bit weird because it's a second derivative. We square the d's, even though you're not really squaring them, and then we write the dt as dt squared. It's symbology. It's really the second derivative with respect to t. I indicated this to you guys last year, that derivatives with respect to t become cumbersome. So there is other notation for this. Another way of writing this is negative q over c minus L q double dot equals 0. Dot notation is a way of shorthand writing derivatives. Several colleges will expect that you already know dot notation. So if you've never seen it before, the dot specifically indicates a derivative with respect to t, not anything else, just time. So I know that my college expected that I knew it, and I did not. And I've talked to former students, and it's UF often expects this, UCF often expects that you know this notation. And many of the students that are going there from out of state will know the notation. I don't know that it's taught in AP Calc, though, is it? Okay. I'm not going to use the notation. I'll stick with this. I just want you guys to be capable. To analyze this, I want to isolate the second derivative. So let's get it by itself. And when we do, we'll get the second derivative of q with respect to t equals minus 1 over LC times q. My understanding is that you probably don't have a mathematical way of solving this. This is a second order differential equation. And unlike calculus, you can't split the derivative and take the integral because it's a derivative of the second order. Order is kind of like polynomials, where we talk about a second order polynomial means polynomial is x squared. An order for a differential equation is the order of the derivative. So no matter how deep your derivative is, you could have a third derivative with respect to time. That'd be a third order differential equation. This is a second order differential equation. And what you have to start thinking about is that a differential equation tells you how two different relationships are related. That's what a differential equation does. In fact, this one says something very specific. It says, if I have a function, q, that is related to time, when I take the derivative twice, I get the original function back times a constant and a negative sign. That's how you read this. So you already know that there are functions that when you take the derivative, you get the original function back. Name one. So I know if my function was e to the, you say x, but we're doing t here. So I'm going to say e to the ct. This function, when I take the first derivative, dq dt, I get a constant and I get the original function, right? If I take the second derivative, the constant comes out again, I still get the original function. This seems like it fits. My second derivative produces the original function times a constant. It doesn't fit though. Why? The negative sign. Can that be fixed by putting a negative sign here? If I take the first derivative, I get the negative sign out the first time. But when I take the second derivative, I get that negative sign again, making it positive. Still doesn't work. Now, this process that we're doing is just called guessing an answer. It's not ideal. There are better things. But if you break out the old differential equation book, chapter 1, guessing an answer. And then the rest of the book is about what happens when you can't guess an answer. So that's what differential equations is about. There are methods here. You'll learn tons of them. But obviously, guessing is probably an inefficient way to do it. But you probably know a function that will work here. Go ahead. Sine or cosine would work, right? We know we take the second derivative of sine, we will get sine back, right? If we get the second derivative of cosine, we get cosine back. And in both cases, we'll get a negative sign during one of those derivatives. So sine or cosine will work. There is a better choice. Which one is better for us to use here, sine or cosine? Okay, I know you all said sine, but this is about charge on the capacitor. Is the capacitor fully charged at time 0, or does the capacitor have 0 charge at time 0? So without a phase shift, which function is at maximum at 0, and which function is at 0 at 0? Cosine would be a better choice here rather than sine.